Hello everyone. Today we will talk about backward Euler discretization of state space models in MATLAB. You will learn one very important technique for discretizing state space models. This technique can be used for developing controllers for dynamics that is stiff, meaning that different state space variables have different time constants, or the time constants of different state space variables can significantly vary. As always, I created a post that nicely summarizes everything that I will explain in this video. This post contains equations and MATLAB codes. Also, I will explain the MATLAB codes for discretizing the dynamics using the backward Euler method. These codes will be posted on my GitHub page. All the links are provided in description below this video. Okay, so let us explain the basic ideas. Let us assume that we have a nonlinear pendulum differential equation, the equation given by the equation 1. And the first step is to introduce the state space variables. So we say that alpha is equal to x1. Alpha is basically the rotation of the pendulum measured from the vertical axis. And we say that x2 is equal to alpha dot. So these are our state space variables. So our state space model will have the form given by the equation 3. x1 dot is equal to x2, and we can obtain that x2 dot is equal to minus k1 times x2 minus k2 sinus x1. We obtain the second equation in the equation 3 from our system dynamics. That is by coupling the system dynamics given by equation 1 with the system of equations given in the equation 2. So the dynamics can be written compactly by the equation 4. And here's the explanation. X is the state space vector, and f of x is a nonlinear vector function representing our dynamics. Now, we can discretize this equation in order to simulate it by using, for example, forward Euler method. However, forward Euler method is usually unstable, and it is not recommended for systems that are stiff. Systems that are stiff have time constants of state space variables that significantly vary in magnitude. For example, one state space variable can have a time constant of 0.1 second, and another state space variable can have time constant of 1000 seconds. These systems appear when you couple multiphysics. That is, when you, for example, have fluid dynamics that is coupled with the structural dynamics, or when you have a structural dynamics that's also coupled with some other physical phenomena. Also, even if the dynamics is not stiff, it is more preferable to use the backward Euler method over the forward Euler method, mainly because the backward Euler method has better stability properties. By applying the backward Euler method to the equation 4, we obtain the equation 6. In equation 6, xk is an approximation of the system's state space variable x at the time instant t is equal k times h, where k is a discrete time instant and h is a discretization constant. We choose the discretization constant by ourselves. Then, xk minus 1 is an approximation of the system state at the discrete time instant k minus 1. H, as I mentioned before, is a discretization constant, and f of xk is nothing less than the vector function f defining the system dynamics evaluated at the time instant k, that is f of xk. Now, having knowledge of xk minus 1, and assuming that this value is computed at the time instant k minus 1, our goal is to solve this system of nonlinear equations. So I said this is a system of nonlinear equations. Well, we can observe that on the left-hand side, on the right-hand side of this equation, we have x of k. Consequently, the equation 6 is a system of nonlinear equations. So, starting from some initial state, x0, at every iteration, k, 1, 2, 3, we can obtain the state sequence x1, x2, x3 by solving the system of nonlinear equations. Now, there are many methods for solving this system. However, in order to solve this system by using MATLAB, we will transform the equation 6 in the form given by the equation 7. That is, we're going to move everything that is on the right-hand side to the left-hand side, and we obtain this equation. Okay, so let us discretize this system in MATLAB by using the Backward-Euler method. The first step is to define the system dynamics. So here is our system dynamics, and I'm going to now switch to MATLAB. So here is my function describing the system dynamics. I'm having a pendulum. So this is our state space equation that you can see over here, defined in the equation 5. I specify the constant k1 equal to 0.1 and k2 equal to 5. Okay, now I will write a function that you can see over here that specifies the discretization method. So what do I have over here? Here's my function. It's called solve backward Euler. Time steps is the number of discretization time steps. It can be 300, 500, 1000. The user specifies this number. Then I have x0, that's my initial state, the starting state. H is discretization constant, and here I have a function handle. Function handle is a parameter that specifies the dynamics. In my case, function handle will be equal to dynamics definition, equal to this function. If you have several functions that you would like to call with a single code, it's always good to parameterize the name of the function. So you can use this code for calling, let's say, a function for discretizing an inverted pendulum or a double inverted pendulum or any other dynamical system. So then what do I define? I define a state trajectory, an empty state trajectory. And over here, I define the optimization parameters. I will use this function, optimOptions in MATLAB, and first I specify the function. I will be using fsolve. Fsolve is a MATLAB function for solving nonlinear system of equation. Then I will use the algorithm, trust region. I don't want to display progress, so I will put here off. I don't want to use a parallel solver. I specify false. So here's one comment. This system is relatively small. It has only 2 state space variables. And if I would specify here true as a parallel option, then my code will execute relatively slowly, since the problem is slow. And when the problem is small, parallel solvers are much slower than the regular solvers. However, if your problem is large, for example, if you have here 10,000 of state space variables, then I suggest you that you specify here use parallel true. And here I specify function tolerances, maximum number of iteration, and stop tolerances. You can play with these parameters. Next, I define my problems. I'm saying that problem options should be equal to this line over here, that is to the variable option fsolve. Then I define the problem objective function. Here is where I do that. And let us jump to the definition of that function. So here is my objective function. So this function is actually equal to the equation 7. So once you write the equation 7, you can easily write this function that specifies basically the left-hand side of this equation. And once I do that, I will define the problem solver. It's equal to fsolve. The next step is to iteratively solve the equation 7. So starting from k equal to 1 and knowing x of 0, I want to compute x of 1. That is, I need to solve a system of nonlinear equations. So O is my time index. It varies from 1 to the total number of time steps. Here I complete, or actually I fill in my state matrix. So the first column of the state matrix will be x0, that is your initial condition. And then I generate the initial guess for solving this equation, the equation 7. So I will be using a simple forward Euler method to find the initial guess. Watch out over here. This problem.x0 is not actually equal to our initial state. Instead, problem.x0 is an initial guess for solving the system of nonlinear equations given by the equation 7. Once I generate this initial guess, I call the function fsolve and I pass as the argument our problem. Then MATLAB goes over here and it calls basically the solver, fsolve, and uses the trust region algorithm to compute the solution. Once I compute a solution, I place it in the second column of the state matrix. Okay, now what happens for O equal to 2? For O equal to 2, again, I generate my initial guess. Then I use this initial guess and I call the function fsolve. Again, MATLAB uses the fsolve function and the trust region algorithm to solve and to compute the third column of our state matrix. And this procedure is repeated until we reach the time steps. One important comment. If you analyze this function, objective function, you will notice the following. You will notice that from this function over here, I can access my columns, actually the columns of the state matrix that are originally defined in this function. So the function objective function is a nested function inside of this bigger solve backward Euler function. And what is a nice property is that this child function, I will call it like that, can access the variables of the parent function. So I do not need to specify here as an input parameter some of the state trajectories or state space variables. I can simply access them from here. Once we have written our functions defining the dynamics, that is dynamics definition and solve backward Euler, it's very important to save them in the same folder. For example, in my case, I saved these two functions in the folder called backward Euler tutorial. And you have to do that for the dynamics definition function. So you need to save it in the same folder. And here you have to make sure that the working folder is actually backward Euler tutorial folder. That is the folder that is being used or that stores these two functions. Another option is to specify in the MATLAB path the folder, the backward Euler folder, because you will have to call these two functions from another function, from our main function. And so here's my main function. It's the driver function. that's being used to simulate the dynamics. First, I clear and pack my workspace. This is always a good practice. Then I define the initial state, in my case 2 and 0, so the angle of rotation will be 2, the initial angle of rotation will be 2 radians, and the velocity will be 0. Here I specify the discretization step of 0.001, and I define the simulation time. This is my simulation time row vector. And first, I will simulate the dynamics using the ODE45 function. I'm using this in order to compare my results and my implementation with the standard MATLAB implementation for discretizing state space models. So let us execute this. Here's the solution. Here's the state trajectory computed by ODE45. Then I simulate the dynamics by using the backward Euler method. I call my function solve backward Euler. I specify the number of discretization step, initial condition, discretization step, and the function handle. I specify my function name that defines the system dynamics. And here it is. So the total number of discretization steps is 10,000, or actually 1,000 in this case. And here's the solution. Now, to plot the solution, we will first compare the results. So I will compute the relative error between the trajectories obtained by using the ODE45 function and the backward Euler method. This is my error simulation, and then I will plot the results. So let's see what do we get. Okay, so here's the first graph. The first graph shows the error evolution in time, the error between the ODE45 and the backward Euler method, and here I can see the state trajectories. Magenta is basically my state trajectory obtained by using the backward Euler method. And the blue, or actually the dark line, the black line, is the state trajectory obtained by using ODE45. You can see that we have very good match and the error is relatively small. Now, let us increase the number of discretization steps in order to see some oscillations. So I will increase the number of discretization steps over here, and I will run my code again. And so let's see what happens. Now this index will go from 1 to 10,000. And over here, it's important to observe the following phenomenon. We can observe that the error will increase over time. That is, the error between trajectories generated by using ODE45 and the backward Euler method. There can be several reasons for that. The first reason can be that, for example, the tolerances are not the same in ODE45 and in the method for discretizing the dynamics by using the backward Euler algorithm. Or it might happen that this discretization step is actually too large, and that the backward Euler method introduces discretization errors, and that these discretization errors grow over time. However, this hypothesis has to be verified by checking the tolerances of ODE45 and the backward Euler method. If the tolerances are the same, then yes, the backward Euler method introduces more errors and it's obviously less accurate. However, this might not necessarily be the case. So let's see what are the results now. Let's see what happens. Here you can see the trajectories. The magenta is basically trajectory computed by using the backward Euler method, and the black line is the trajectory obtained by using the ODE45. We can see that we still have a good match, relatively good match, and the error increases over time. We can decrease this error, for example, by decreasing the discretization step. However, if we decrease the discretization step, we need to increase the discretization time. Now, someone might ask me over here, so why do we need to use this method when OD45 is a more accurate and a faster method? Well, when you want to develop a controller, you need some analytical form of your dynamics. If you have a stiff dynamics, you will assume the backward Euler dynamics. So you will assume that dynamics is given in this form. Now, to develop any type of a controller or any type of algorithm for verifying the stability of the system, at certain point you will have to simulate these dynamics. You cannot simulate these dynamics using any method. You need to use actually fsolve function, and you might be able to get even better result if you use different type of an algorithm. Okay, that would be all for today. I hope that you like this video. If you like the videos I make, please subscribe or support my channel. Thank you very much and have a nice day.